Hello, everybody. So the first problem, or not the first problem, the lab that we will be doing today is decision trees. And in the decision trees, firstly, let's understand the model and the applications of it. On what kind of problems we can implement the decision trees? One, and is it supervised machine learning or unsupervised machine learning? The decision trees fall into which family? All right.
Supervised.
It is supervised because we will be having labeled data. All right. And for what kind of problems we can implement decision trees? We can implement for them for classification problems. And we can implement them for regression also. All right. Regression also, we can get the numerical values between a confidence interval. All right. For today's understanding the decision trees, they are like, think of them like trees that we have learned in DSAs. All right. Okay. Now, to understand in and out of the decision trees, firstly, let's talk about a data. Today, we are given a data of animal, color, and the label of the element. No, sorry, animal is the label actually. Color and height is another feature which is given to us. Then we have the color like gray, yellow, yellow. Two types of colors. One is gray, one is yellow. Height greater than 10 feet. Animal, elephant. All right. Less than 10 feet, yellow. And the animal is tiger. Gray, less than or equal to 10 feet is hippo. So and so forth. All right. So data like this. Cool. Now, think of it like a X matrix which is given to us, input, feature, label. Just to summarize, we have 3 elephants, 3 hippo, 2 giraffe, and 2 tigers. The giraffe and tiger are yellow in color. These both are gray in color. Alleys. The height of the elephant is greater than or equal to 10 feet. Height of giraffe is also greater than or equal to 10 feet. Height of tiger is less than 10 feet. And height of hippo is also less than 10 feet. What we have to do is we have to classify whether the animal is an elephant or a hippo or a giraffe or a tiger. So imagine at the root stump or the root node, we have all these 3 elephant, 3 hippo, 2 giraffe, and 2 tiger. Now I have to take a decision. Imagine I am taking a random decision right now. If I take a random decision right now, based upon color, whether the color is yellow or not. If the color is yellow, then in this decision stump or the node, what will be the animals that I will be having? I will be having 2 giraffes and 2 tigers. All right. If I take this, then there will be 3 hippos and 3 elephants. Now the next criteria for decision split can be the height. If I take the height, then that is greater than or equal to 10 feet. Then I will be having two giraffes over here and the two tigers over here. I will be having the three hippos. If it is greater than 10 feet, then three elephants over there. Right? Less than 10 feet. And this is the way that we can have the decision tree. One of the ways that I can have the decision tree. Till the time I do not have the pure nodes. All right? Till the time I do not have the decisions. Now, at this place, I could have the split based upon the colors, or I could have it based upon the height. These are, right now we had just two features, age, or not age, the height and the color. I will be having multiple features in my data. How do you decide at which level that we have to split based on this criteria? We have to take a decision for that. And based upon what should we take the decision? Based upon a number. There are two classification, or there are two criteria, not classification only. We can do it for regression also. One is Gini impurity. Another one is entropy. With both these indices, we can calculate something called information gain. But let's understand these two indices at the conceptual level first. The purpose of both these indices is to find one thing and one thing only. That is, what is the randomness? At a particular node, what is the randomness in my data? Remember, we have to go from the most random to the pure nodes. If I am making a split, then it reduces the randomness. But by how much randomness is reduced is calculated using Gini impurity index as well as the entropy. We can use either of them. We'll see on what kind of data we can use the Gini, on what kind of data we can use the entropy. But Gini impurity at a particular node or Gini index at a particular node just measures how much random are you node. Hey node, are you, how much random are you? Let's say the randomness of this node is 10 and the randomness of this node is 5. The randomness of this node is 2. Just imaginary numbers. Then the information gain will be 10 minus 5 minus 2. That is, I have gained a information gain of 2 points. That is the criteria on which we will be taking the decisions. Now, this is a sample decision tree that we have built. Before going into exactly how we will be calculating the Gini index and the entropy for a particular decision tree, first let's understand, we have already talked about the applications of decision trees. Let's talk about the strengths and the weaknesses of the strength and weakness of the decision trees. Strengths and weakness. Just by looking at this model, can somebody tell me what can be the strengths? One is it's visually visualize. We can visualize it. It's simple. The second strength is I do not need to scale the data. I do not need to scale the numerical variables or numerical features or encode the categorical variables. All right. So no scaling required. Till now, in the last week, we have talked about the models, whether it is classification models, whether it is regression models. We have talked about models which had linear boundary. Linear regression, logistic regression, linear model. Makes sense? We had talked about the models which were linear in nature. But today, the decision trees are non-linear. They can have the linear boundary, but they can have the non-linear boundary also. I'm not worried about whether the boundary is linear or not. Doesn't matter, because if I'm taking the decisions, my points of my tiger, giraffe can be anywhere in the plane. In fact, the data that we will be using is today in two classes will be like this. The boundary will be a circle and 0, 0, 0, 0, 0, 0, or whatever. One class right here and the other class right here. These are some of the strengths of the decision trees. But with strengths comes the weaknesses. What are the weaknesses of decision tree? The very glaring weakness of the decision tree is overfitting. They overfit very easily. Especially if the depth increases, then basically the model remembers the training data, the training labels. If a little bit of data leakage, the overfitting, that is another kind of overfitting. Remember, overfitting can happen due to the data leakage, or it can happen because the model is too complex or the model has already learned the data. So both these criteria of data leakage and model remembering the data, we will observe in today's lab. One weakness is overfitting. What is the other weakness?
I mean, like how we are like making these trees, like we are making multiple trees, essentially. Like we are taking, for example, one can be, we are deciding on color, another can be deciding on another feature. So like we are kind of like, how would I say, a brute force way of like trying all possibilities.
Not brute force, they are greedy in nature. They are greedy in nature. Once we are taking a decision at a particular node, we are just worried about that node, that how much the split at this place is going to reduce the impurity in my data. All right. And we are just worried about that node only, that stump only. So they are greedy in nature. It doesn't look at the exhaustive picture or the overall picture. That decision right here, how is it going to affect the decisions at the further stumps? Now, this overfitting we can overcome in case of decision trees. We can overcome the weakness of overfitting by using multiple decision trees in parallel or in a sequential manner. That is, the advanced decision tree models like XGBoost or Random Forest will come into the picture, because this is one of the glaring weaknesses of the decision tree models. These are the strengths and the weaknesses of the decision trees. Now we have covered. Anybody, any questions till now? All right, let's come to the tactics. How do we calculate the Gini index or the Gini impurity of a particular node? All right. The Gini index is given by 1 minus P naught square plus P1 square. If I have just two classes, if I have the binary classification at a particular node, then it is given by the left baby and the right baby. 0 class, 1 class. All right. So if this is given like this, it is basically 1 minus sigma of Pi's, where I is 1 to n, where 1 to n are the all classes that we have at a particular node. I can have more than binary split also, right? What if I had 3 colors? Then I can have yellow, gray, red. Now, in order to calculate the Gini impurity, let's calculate the Gini impurity. I have two options. One is I split on the color, and the next is I split on the height, or other way around. I split on the height first and then the color. We'll calculate the Gini index of both the scenarios and we'll take a decision accordingly. If I want to calculate the overall probability over here, 1 minus probability of, remember the weighted probability. What is the probability of having an elephant?
3 into 1 by 4.
3 into 1 by 4. Why?
1.
I have
We
3
have
elephants. Total 10
Yeah.
elephants. 10. No? So 3 by 10, right?
Yeah, 3 by 10.
3
Yeah.
by 10.
All right. What is the probability of having a hippo? 3 by 10 also. Giraffe, 2 by 10. And what is the probability of having a tiger? 2 by 10 as well. So if I take 3 by 10 square, all right, into, not into, plus 3 by 10 square, plus 2 by 10 square, plus 2 by 10 square. What will be the number at this place? It will be, let me check. That is 0.3 square, 0.3 square, 0.2 square, 0.2 square. That will be equal to 1 minus the calculated value will be 0.74. Make sense? So at the root, I have the randomness value, that is the Gini impurity, as 0.74. Now, if I split it on yellow and gray right here, color, then I have to calculate the Gini impurity of this one. That is, for 2, I'm going to delete this, okay? 1 minus, what is the impurity of the giraffes over here, or the probability of the giraffes over here?
Half.
2 by 4.
Half, that is 2 by 4. All right. And that is 0.5 square plus 0.5 square. Cool. That is going to give us 1 minus 0.25 plus 0.25, right? That is 0.5. So the Gini impurity at this place will be 0.5. How about this? This will also be 0.5. Make sense? Now, if I want to calculate what is the information gain over here from this to this split, then it is earlier Gini index minus the Gini index of the left baby, Gini index of the right baby, but the weighted ones, right? How much is the weight of the left one? 4 by 10. into 0.5 minus 6 by 10 into 0.5. All right. If I take that, then this value will be equal to this will be equal to 0.74 and this will be 10 only minus. So 0.4 into 0.6 into 0.5 only, which is 0.24. All right. So the split by color at this position gives us an information gain of 0.24. Let me take the questions now. Yes, Akshay, go ahead. What's your question?
I just wanted to understand, why do we square the probabilities?
It's by, that's how we measure it. That's how we measure the impurity. All right. It's just a measuring index. We can measure it other way around also. That's with
Okay.
entropies also. Make sense?
Okay.
All right. All right. So the impurity information gain, if I split by color, is this much, 0.24. Let's take the other split. If I have the split by height, all right. If the split by height greater than or equal to 10 feet, then what all animals I'll be having? 3 elephant over here and 2 giraffe over here. If I have lesser than 10 feet, 3 hippos and 2 tigers, I'm just worried about this decision stump right now. Initial Gini impurity 0.74. And now over here, it will be 3 by 5 will be the probability for the elephant. So 1 minus 3 by 5 whole square plus 2 by 5 whole square. Same thing. 1 minus 3 by 5 whole square plus 2 by 5 whole square. All right. So if I take 6 by 10 over here, 1 minus 0.6 square plus 0.4 square, which is equal to 1 minus 0.36, 0.16, which is 0.42. All right. And if I take 0.1 minus 0.42 is equal to 0.58. So the Gini impurity over here is 0.58. Let me just check the numbers. I might be making a mistake.
No, I think 48.
0.48. You are absolutely correct. All right. 0.48. This is
That's 0.52.
0.52. All right. So 0.48. So the Gini index over here will be, or the degree of randomness over here will be 0.48. Over here, it will again be 0.48. How much is the information gain? Earlier it was 0.24. Now the information gain is 0.74 minus the weighted average of this, that is 5 by 10 into 0.48 plus 5 by 10 divided into 0.48. That is going to be equal to 0.74 minus 0.48, which is equal to 0.26. So this split gives us a information gain of 0.26. The earlier one gave us an information gain of 0.24. So which split is better? Apparently this one. That's how we choose that on which feature I should be doing a split in the decision tree. We do not take random decisions. Now, one of the ways that we can calculate for each feature, if I do a split, what will be the Gini impurity and the information gain? And Gini impurity can be measured 1 minus sigma of probabilities, square of probabilities. Another way that we can look at the randomness is, randomness means entropy only. Then it can be P naught log of P naught plus P1 log of P1, or sigma of probability and log of probabilities, is the way that we can calculate the entropies. Have you seen this formula before, Samit?
Expected
Binary
and
cross into
Binary
Cross
cross
en-
entropy. Hitesh is absolutely correct. It's BC. If I have a binary split, then P naught is nothing but 1 minus P1. So, or P1 is nothing but 1 minus P naught. P naught log of P naught plus 1 minus P naught log of 1 minus P naught, which is BC. Now you
Yes.
understand entropy. Makes sense? So now we can measure the Gini index or the cross entropy, binary entropy like this. At each and every stump, we'll take a greedy decision that how much is our information gain, how much a decision is reducing the randomness in my data, and we'll carry on from there. We will do the decisions for all the features. We'll not say that, okay, I'll just choose this feature or this feature. We'll explore the information gain on each and every feature. Till the time where our impurities become, I have a clear-cut classification, or I have a significant range of the classifications. Does it make sense? Anybody, any questions? Let's try to get into the calculation of the thing into the lab and look at some of the.
I have one question regarding entropy. Like, if we'll calculate this,
Mhm,
so if we get some number,
mhm.
then how do we decide? Like, more the randomness, we don't want that, right?
Yes, we do not want randomness. Information gain sees that, okay, from 0.74, you were able to reduce, you had an information gain of 0.26, so you were able to reduce your randomness in your data by 0.26. Make sense? I need to
Yeah,
have, I need to have less
it's different.
randomness, less randomness, less weighted randomness of all these combined babies over here.
Okay, and less entropy, less information gain.
Nope. Less impurity, it means more information gain.
Okay.
Make sense?
More information gain and less
Better.
entropy.
More information gain, less entropy. All right. Information gain is nothing but the earlier Gini impurity at the parent minus the impurity at the babies.
Okay, yeah.
So let's take the initial data over here. The initial data in the lab is we want to build a model like this. The violets represents the ones and the yellows represents the 0, or other way around. I just want to call them class 0 and class 1. Cool. Now, I am making a non-linear just because our data, we want to show that, okay, it works on the non-linear boundaries as well. Decision tree is a great model for exploring the data on the which have non-linear boundaries. We have a standard check function. And then when we have is we are creating a uniform distribution from -2 to 2. We have not assigned them labels yet. We are creating number of samples n and 2 features. All right. Then what we are doing is we are creating a circle boundary. Basically, imagine this as the circle. We are taking its radius. Radius is nothing but the square root of the 2 features that we have. Makes sense? You can do anything else also. All right. You can take bigger circle also. For the purpose of our demonstration, we have taken the square root of the first feature and the square root of the first square of the square, some squares, basically the norms. All right, we have taken the norms of the features, and that we have taken as the radius. All right, then what we are doing is for the real world, because if everything is yellow over here and everything is violet over here, it doesn't represent our real world data. We are flipping some of the labels. All right, firstly, we are assigning the labels that if anywhere the R is lesser than 1, that is between this circle, if it is, then what we are assigning it is a 0 or 1. All right, we are assigning the yellows as 1. If the radius is lesser than 1, then we are assigning it a label equal to 1. Rest everything is 0. Cool. So everything within this circle will be having a particular, everything outside of this circle will be having a particular class. But it will be the pure class. I want to bring in some real world noise. And how do I bring this real world noise? Is by flipping some of the labels. All right. We have a random number generator. We have different values between 0 to 1 for them. Anywhere where the value is lesser than 0, 0.5, I am flipping its label. Basically, it gives us a mask. If I print flip over here, it should be giving us a label, a vector of true and falses. All right. Once we are mounting that mask onto my Y, that for certain indices, which are very lesser, 5% only, flip the label. Basically, if it was, earlier it was 1, then now it is equal to 0. So that I can have in between dots over here. And between the yellow area also, I have some violet dots, 5% only. All right. So we are flipping their label from 1 to 0. If earlier it was 1, now it is 1 minus. Earlier it was 0, now it is 1 minus 0. That is 1. Earlier it was 1, then it is now 1 minus 1, which is equal to 0. So we have flipped its label. All right. And it is a non-linear data that we have made. We have random number generation. We are, mixing it up, mixing all the indices. Then we are taking a training data, 70% training data, and 30% as the validation data, test data. This is what the libraries also do. They just permute, then they have 70% of the first 70% of the data as the training data and the validation data from 70% onwards. If you specify 70% as your split, train test split, okay? Now this is what we are defining as the training data. It will be having, X training will be having only the training features only, no label. The label will be Y training. And the validation features or the X matrix validation and the validation labels. Makes sense. Now what we are going to do is, let's just run it. All right, shapes are okay. This is what I was showing you, and this is how, this is the figure. You can see it also. All right, 0.24 and 0.26, just for your reference purposes when you are doing the things. And the first task that we have to do is calculate the Gini. Okay, before going to the Gini and entropy, how do we calculate them? We have to discuss which one is better among Gini and entropy. Both are randomness measures. Both will be calculating the information gains. Which one is better? Which one is not? Remember, whenever we are talking in the
Entropy is
terms of, when we are talking about the machine learning or AI, at that time, there are certain things which matter. One is the tactical level things, one is the data level things, one is the model level things. The third one is the third one, and very important one.
Computational.
Computation.
Computational, absolutely. Compute. All right. Compute wise, which one is faster?
I mean, entropy
Entropy.
is calculation.
Entropy,
so
why?
Log because it's using logs.
Globe is using log, so it's slow. Log calculations are slow.
Log calculations are slow. All right. Log calculations are slow. That's why in production, mainly the Gini index is used. Make sense? All right. Now let's go to the, how do we calculate the Gini? We have already seen it. So let's take, if we are given y, then y is equal to just a guardrail, np dot as array of y, and data type d type is equal to, I can show the data type like this also, okay? I can show np dot int 64, or I can do it in the commas like this also, okay? And then we have to calculate the p naught, p0. How do I calculate the p0? P0 means what? Ones where the labels are 0. Ones where the labels are 0. Make sense? If I want to take the number of places where y is equal to 0 divided by total number of places, total number of samples. Samples where y is 0 and total number of samples. I can do np dot sum and divide it by the total size of y. I can do that, or I can do np dot mean where y is equal to 0. P1 is equal to nothing but 1 minus p naught. If I want to calculate, then return float of what? 1 minus sigma of p naught into p naught, p1 into p1 square, plus p naught into p naught. Oops. I can have one exception over here also. If my y size is equal to 0. All right. Then what? Quantity, return. Impurity is 0. All right. If I run this, let's see what are the mistakes. It works perfectly fine. Basically, the check was that if I have 5 zeros and 5 ones in my data, its Gini impurity should be 0.5, right? Half. Randomness is half. Make sense? Then I will be having the 0.5 minus 0.5. I'm checking it is very smaller than that of the numerical stability element. Make sense? Akshay, did you understand it? If I'm taking the square of the probabilities, then I will be having the randomness as half. For example, 1 minus 0.5 square plus 0.5. I could not do 1 minus 0.5 minus 0.5. I cannot say the randomness is 0.
Right.
If I take the squares over it, then I will be able to say that half of the elements are 0, half of the elements are 1. In English, it means that I have 50-50 split. Make sense? That is the 50% impurity in my data, in my star. Make sense? That's why we are taking the squares. We are not taking just the numbers, because the impurity is not 0. Impurity is 50% impurity. All right. All right. Now we have taken the Gini. I just want to look at the, okay, y dot size equal to 0, then we are returning 0. Perfectly fine. If I have to calculate the entropy can be calculated. Again, just a guardrail over here. And then P naught will be equal to, again, this thing only. And P1 will be this thing only. Now, if my okay, I have to return what? I have to return float of minus of float of P naught into log of P naught log 2 P naught and plus P1 log of P1 into log of P1 log to the base 2 P1. Huh? Okay. So if I try to run this, log 2 is not defined. I'll take log only. Okay. Log is np dot log. Np dot log. All right. If I run this, entropy half, we are making some mistake somewhere.
You're not, oh, base was missing.
Say that again.
I was saying like base 2 was missed. So
All right. We are not taking base 2. If I take base 2, then it is fine. But I want to do some of the things over here. If my P naught is equal to 0, then what should I do? I should be doing a check over here. P naught is equal to 0. Then I should be returning 0. Why should I do that? That is this guardrail over here. Not only this, I should be doing this, but along with that, I should be doing this also. Can somebody tell me why?
It means like no randomness. If
log
Okay,
0
yes, it does. If P naught is equal to 0, okay, that's fine. Yeah, in English it means no randomness. But
log
I could have
no
given it to.
information, no information gain, right? If there is no randomness, like they are in the same class.
But if I had given it to this formula, all right,
Log
then
0 is infinite.
log 0 is minus infinity. Makes sense? And we would have a numerically unstable function. All right. So at the function level, it is because of the numerical stability. All right. Just a moment. All right. Why do we use log 2 rather than log only? And this is actually related to the information theory. All right. In the information theory or information gains, we use the log 2 rather than simple logs. All right. The reason is, so the formula is actually log 2 only. Okay. The reason in information theory we use the log 2s is because the log 2s are more numerically stable than the logs, than the natural logs, and computationally more fast. All right. Still, they are slower than that of the Gini impurity. Gini index, sorry. All right, because that one doesn't have logs. All right, now what we are going to do is we are going to see that how do we choose a feature? If I have many features, for example, we have calculated the Gini index and the entropy. But next thing that we have to do is the best split. Best split is based upon what? The information gain. If we have to calculate the information gain, then how do we calculate the information gain? Then I have the parent, which is equal to y. I can calculate. Firstly, I'll define the function. The function is my Gini if my criteria is equal to Gini. Else, it will be equal to the entropy. All right. The parent will be giving me the Gini index of the function of y. If I just give the labels of y, that is the parent, then I should be having the Gini index over here. How do I get the Gini index of the left baby? Left baby will be equal to function of my y left. Imagine you already have, we will see how to hire the y left and the y right. All right. But imagine if you already have it, we'll see how we do it. Divide the two babies. All right. But if you have the left babies and the right baby labels, then you want to calculate the Gini index or Gini impurity or the entropy. So we are giving y left and y right over here. And how do I calculate the information gain? Return float of parent.
Minus sum of left and right.
This will give you the impurities, but they will not give you the weighted impurities, right? Weighted of left. Remember, we just didn't do this thing. That is what. That if we had 0.5 over here and 0.5 over here, we didn't do that. We did 0.74 minus 0.51. That will lead to a negative information gain. We cannot have negative. We have to have the weighted over here, right? 5 by 10 and 5 by 10 is what we did. Make sense? That's how we got 0.24. So we need the weighted averages, weighted probabilities, not the averages. So weighted for left will be left baby's probability into what? How many elements
Y
of the
left
left?
dot size
Perfect. Y left dot size divided by
by
n.
y dot size.
All right. If I take the n as y dot size. And how do I get the weighted for right? Will be equal to right baby probability and y right divided by the size of the parent. All right. So parent minus WL plus WR. All right. Okay. If I'm running this, let's see. The information gain will be equal to 0.003. Let's check it with my solution. Is it 0.003 only? Absolutely correct. So whatever we are writing over here is correct. And for the sake of this y left and y right split, for my information gain function, just for the test purposes, what they did was they took a feature 0, j is equal to 0, zeroth feature, all the rows of the zeroth features, we took the median of them. We took the median of them, and then for the threshold, we took the median of them. And anything for the jth feature, if it is lesser than the threshold, we defined it one label, that is the left label. It will be giving us a mask. Anything except left is the right baby. Now we are on the training data, we are putting the left mask, which will be giving me the labels of the y left. And y right will be giving me the labels of the right baby stump of the decision tree. And criteria we are mentioning is Gini. And the information gain should be greater than or equal to 0. Make sense? So for the purposes of this, they are taking the 0th. Right now, they are hard coding the feature. We will explore all the days. Make sense? So this is the way that we can calculate the information gain from the parent and the babies. The next step is that find the best feature and the best threshold. We have to return 3 things. One is, which is the feature that on which I will be doing the split? What should be the threshold of that split? Make sense? What threshold defines what is the left baby and what is the right baby? And how much is the information gain on that split? So not only the decision of my which feature to choose, but also the threshold, that what is the best threshold among that feature. For example, if we have the data like age, which is For the sake of discussion, I am taking it as sorted 11, 13, 15, 16, all right, 17, or 18, then 20, then 22. If this is the age, I have other features also. For example, height. Height is 180, 181, 184. We have everybody who is very tall. 190, 192, 193. Firstly, I'll be iterating on each and every feature to see which feature to choose. And among those features, I have to explore each and every threshold. So for example, what is the threshold that I should be taking in this age? Because based upon the threshold, I will be able to define what's the parent, how much is the left baby, how much is the right baby. If I take the threshold as 11 only, then everybody is going to be on right baby. I have to choose the best threshold. And at that feature, at that threshold, how much is the gain? Is what we have to calculate. So firstly, I will take all the number of samples and the number of dimensions of my X, which is going to be X dot shape. Cool. Now the next step that we have to do is we have to iterate over all the features. I'll take the best split as a tuple in which my -1 feature, I've taken -1, none threshold, and -1 as the information gain initially. We'll keep updating this tuple. All right. Then we have to iterate over the range J, that is feature for range, for J in range, all the dimensions. Oops, I'm in the Java word now. All right. For each feature, we have to calculate the thresholds. All right. Let's say the thresholds is equal to some list. All right. Then for each threshold, in thresholds, we have to calculate the Jingbang. Jingbang means what? The information gain, info gain. That is information gain. On what? Information gain requires three things: Y, Y left, Y right, and the criteria. All right. So right here, information gain, Y, Y left, Y right, and the criteria is already given us to, we are taking the Gini criteria. But we have to calculate, we are already given Y, we have to calculate the Y left, we have to calculate the Y right. For that, firstly, I'll take the left. Left will be nothing but at a particular threshold, anything, the X feature, sorry, the X matrix, the jth feature in that, if it is lesser than or equal to the threshold, that will be my left data. The right data will be nothing but tilde of left. All right. And Y left, Y right will be nothing but Y of left. And this will be Y of right. Cool. So I can let go of this. But the main bone for contention is, how do I get the thresholds for jth feature? Firstly, I'll take the values. Values of my jth feature will be equal to X for each row, jth column. All right. Now, in order to take the thresholds, we can have different strategies. For me, right now, the strategy that I'm taking is, remember, it is a very smart decision if I can take the threshold among these values only. Or some combination of these values. I'll take the combination as this. That is 11, 13, 16, 18, 20, and another array of 13, 16, 18, 20, 22. And I'll take the thresholds like 11 plus 13 divided by 2. And the next threshold as 13 plus 16 divided by 2. That is the average of the consecutive values. 16 plus 18 divided by 2. So and so forth. So I'll take the values. Firstly, I may need to make sure that these values are unique. np.unique. All right. Of all these values. Then in order to take the thresholds will be what? That is values from 0 to, except the last one, plus values from 1 to end, divided by 2. This is exactly what we are showing on the whiteboard. First array, second array, take the sum of them, divided by 2. So it will give us a vector, which will be 12, and this one will be 14.5. This one will be equal to 17. This one will be equal to 19. This will only be equal to 20. All right. And those values is what we are using as a threshold. Okay. Now what we are going to do is, few things that I am forgetting over here is, one, if the values dot size is lesser than 2, then what should I do? Think in English it means what? Values dot size is lesser than 2.
Just one value, so threshold will be that value.
Just one value and threshold will be one value. And will I be having any impurity over there? Everything is the
No.
same. I will not be having an impurity. So what are we splitting? Nada. So don't do anything, continue. Make sense? All right, now if I have thresholds, if I calculate what is the current information gain at a particular feature, at a particular threshold, what is the information gain? If that information gain is greater than the best's second index. Remember, at the second index, we are having the gain. If this information is greater than the already existing information gain, then who becomes my best? My best becomes a tuple of three things. That is the current feature, jth feature, the current threshold, T, and the current threshold or current information, that is the current. And in the end, all I will return is this tuple of bests. Because the best split should be giving us the three things: the feature, its threshold, and the gain. All right. And in the end, we are just checking that the gain is non-negative. If I try to run this, let's see what are the mistakes that I'm doing. It passes all the test cases, 0, 0.026 and 0.033. All right. If I load the solution in the editor, it should be giving me the same answer. Anybody, any questions till now? Very straightforward, right? Yes, Ajay, go ahead. What's the question?
Yeah, so do we sort the values, the age column?
You do not need
No?
to sort the. You do not need to sort. If you sort, you can. If you want to sort, you can sort. But if you do not need to sort, you can. I can just have 11 and 21 over here. All right, and 16 and 19 over here. All right. Basically, my idea is to try different thresholds. All right.
Okay, so there is no pattern. We can choose whatever we want.
You can just choose whatever pattern that you want. Make sense? If you sort it, but the sorting is going to take time, no? All right. Each and every feature that you are sorting, it is going to take time. All right. Or you can take maximum and minimum and you can try all the thresholds between them. That is also going to be a little bit expensive. All right. But I'll reserve this question that, okay, if we want to sort, I don't think so we need to sort. Do we need to sort? I don't think so.
This, like in the exercise XTR, YTR, like how we have taken that, it depends on, right? Like what is the data? I mean,
They are
like-
saying that, okay, if you sort it, then it is better. All right. All right. If we sort it, it's better. All right. But there is a cost associated with it. Yes, Sonal, go ahead. What's your question?
I was asking like in that function you have called XTR, YTR.
Mhm.
So like how is that defined? Like
That
how
we had-
how does that
That we
data
had that we had defined over here, no? In the first over here, we had taken 70% in the training data and 30% in the validation data, right?
okay, and these are like normal only, right? Standard normals.
These are
Like
this
not
is uniform.
data.
Uniform between -2 and 2. -2 and 2.
So I was saying like this will be sorted itself in start. Like looks
Yeah.
like
Uh,
so here we don't need sort maybe.
okay. Print X. Okay, let's do it. Print X for the first 10 rows. You might be correct, but let's see. Not really. All right. So first feature, second feature. It is a uniform data, randomly generated uniform data. Cool.
But
Ideally, I
before
should.
making the split, we are permuting it, right? Anyways.
So
So
if
it doesn't have to be sorted.
that's a great point again. I love these discussions in the class. So if it is, let's print the training data. He might be right. All right. X training over here. All right. Not still. No. All right. Still random. Makes sense, Hitesh? So we are permitting it. Still, it is permutation, random permutations. Indices. I'm just putting a mask on the indices. If the initial data is not sorted, then we are putting just the indices. It will give me the indices. Okay, what are the indices? 0, 1, 2, 3, 4. But the numbers over there are not sorted yet. All right. Ideally, they say that we should be sorting it. In the next lab, probably I should be sorting it. Okay. I'll see what are the repercussions. All right. For now, I'm going with this on. All right. And this is the way that we'll be getting the best split, which feature, which threshold. All right. Now let's go to the next one, that we are going to train a stump. All right. We are going to make a prediction at a stump, basically. We are going to fit the model. And in the decision tree, so we have to calculate at a particular time. If I make this decision, this feature, this threshold, what will be the resulting labels? And then we will calculate what is the accuracy. As soon as we go down, the accuracy should increase. With more depth, the accuracy should increase. For example, in the next task, when we are exploring the different depths, with each increasing depth, you will see that the the accuracy should increase. All right. But right now, at a particular depth, why I'm raising my own hand? Lower your hand. How do I raise? Okay. So at a particular stump, at a particular decision tree, if I calculate the best split, best feature, best threshold, best information gain, then what will be the resulting labels of my training and test data? All right. So if I want to predict, then I need to have few things. That is, I need to calculate the best split, right? Best split requires what? Best split requires X train. That is XY. Let's call it X train. All right. And Y. Let's call it train. and the criteria. All right. Then I need to have the best split for the test also. X test and another one. Okay. Okay, we'll see. All right. So firstly, if I want to have the best split, this should be giving me three things. The jth feature, the threshold, and I do not need to use that information gain. We'll be getting the information gain also. All right. Now I need to calculate what is the label of my. If I have the jth feature and the threshold is t, then firstly, x train left. Okay, x left. Then I need to have y left. Then I need to have x right. Then I need to have white light right also. Okay. So if I have the jth index, so x, all the rows, jth column, if it is lesser than or equal to threshold, and x right is nothing but x of x train, x train tilde of right, left, no? So tilde of left, how do I take it? X train tilde of left. All right, this is incorrect. I should be taking the left as it will be giving us a mask, right? And then mask is what we have to mount on the X train. So this should be giving me a mask. Now mask is what we have to mount on the X train left. And right will be equal to tilde of left, so X right. And y of my tilde of left and y of my left. There is no y, so it is y train. Cool. Okay, now what we are going to do is y left and y right is what we have to find out. X train and x. I don't know whether we require this or not. I might not be requiring it, then I'll delete it. Then we have to do it on the test. Determine labels on test. How do I determine the labels on test? In order to determine the labels on test, I have the X test. The left, X test left is equal to X test, X test. The left, where the threshold is lesser than the calculated threshold. But these are the labels on the training data only, right? So left will be equal to, left for test will be equal to X test for all the features or for all the samples, the jth feature of my X test is lesser than or equal to threshold. All right, and over here left test and X right test for the test data will be X test tilde of left test all right, and then the y left of test is what we have to find out, and y right of my test that we have to find out. and we have to give out y hat of training and y hat of validation. Test is nothing but the validation. So right of test will be equal to for the training data, we already have the samples. Is it going to be equal to y of left and y of right? Oops, did I do something? Y of right. All right. Okay. And then we have to return
It should be like 14 should be y test.
just a moment. Y hat of training. Okay, y hat of training and y hat for test. We have to calculate the y hats also. For that, I have to stack them up. All right. So y hat of training will be equal to nothing but stacked version of np dot horizontal stack or vertical stack. P stack of two things, that is the y left and the y right. I'll come to your question. Lohit, y hat training test will be equal to vertical stack of y left test and y right test. Okay, and the accuracy can be defined. Return np dot mean of if my y is equal to actual y is equal to predicted y that we have on it. Just a more, let's see what are the mistakes that I'm doing. All right, JT, that is fine. Left and right. All right, left labels. I'm just taking a mean. I don't need this x left and x right actually. I just need the labels already. And okay, they are just taking the y hats only directly. I don't need this. I don't need this also, remember. And we can do this also, stack them up also. And okay, let's just do this only. All right. So the left labels are on the training data if the label is lesser than or equal to the threshold. So right will be equal to tilde of left. The left label will be equal to if we take the training left's data and we take mean and round off it. All right. Why? Because if I take the mean, then it may be possible that if I have 0, 1, 1, 1, all right, then 3 by 4, I will be having 0.75, right? Basically, I am looking at all the left. They will be having certain labels, right? This is 0, 1, 1, 1, 1, 0, 4 by 6. Make sense? So all the right labels, this is the right data, will be having 4 by 6, which is equal to 2 by 3, which is equal to 0.66. It means the label of all of them should be round of 0.66, which is basically equal to 1. Make sense? If I take the mean of these two, for all the left indices, their label should be 2 by 6, which is equal to 0.33, which I rounded, then it will be 0. Make sense? The same thing that we are taking over here, that if I take the left label and the right label will be equal to round of the mean, integer value of that. Once we have the left label and the right label calculated on the training data, then we have to mount that on the test data, right? So how do I take the test? Left will be equal to where the threshold is lesser than or equal to t. That is the test left, which we were doing. Test left, the right will be equal to nothing but tilde of test right, if I have to write it, will be equal to tilde of test left. Wherever for that feature, the test data for that feature, the threshold is lesser than. And I will be giving the y hat. That is, this is nothing, right? Us writing y test, y for y test left is what we were writing earlier, which is basically y hat. I do not need to stack it later on. I am already taking the y hat, which is basically an empty array of the size of the left. All right. Number of features, number of labels of my test data will be equal to what? Shape of the text, X test, right? We are initiating it with zeros. Earlier we were taking them separate, then we were stacking them. Rather than doing that, what we can do is we can take the number of take an array of zeros, and then test left is nothing but the left label, and I'm assigning the right one as the right label. Earlier we were doing this. We didn't need to take the split of the x, the matrix. All right. I just need to see the indices belonging to the left and the right. All right. We'll be giving the y hat. If we have the predicted probability, the accuracy can be given by mean of y and y hat. That is training my stump at a particular place. If I try to run this code now, this should be giving us a training accuracy of 0.76 and a validation accuracy of 0.75. Not perfectly accurate. And the accuracy is not that high also. Why? Because it may be possible that the current depth in the tree, the depth of the stump might be towards the upper side of the tree. All right. Now, if we try to explore different depths, we are using the sklearn decision classifier over here. Basically, the classifier is nothing but inbuilt under the hood like this. Prediction at a particular stump, the Gini impurity calculation, the entropy, the information gain, and choosing the best feature. If I have the classifier like this, which is basically all the code that we have written up, and we are trying different depth. If I train the classifier with depth 1, with depth 2, with depth 3, 4, 5, 6, 7, 8, 9, 10. All right. And for the sake of, yes, Lohit, go ahead. What's your question?
Isn't like depth decided on features? Like, why are we giving it a list here? Essentially, I'm confused.
Depth decided on features means?
Like, we are firstly trying to decide the optimal feature,
For example,
right?
over here, what is the depth decided on features?
Oh, sorry. No, on the decisions. Like, we actually try to find the optimal decision, right? Like, for example, color, and then height, right?
Okay. So if the color, if the greater than or equal to 10 feet gave me the better decision split over here. All right.
Right.
So we'll
Right.
make that decision, right?
Right.
All right. So at depth 1, this will be the split that I will be having. That is 3 elephant and 2 giraffe and 3 hippo and 2 tigers. Correct? This is at
Right.
depth 1, right? At depth 1, how much is our accuracy in our data? Make sense? Are you thinking that we have to have only every time we have to have depth 2 only?
No, but in this, like I'm just looking at the list, like depth of 7, like it's like if we are just taking this
What
data
is the depth of the tree has to do with the list length?
on these features, like we make a decision, right? What's it like? We actually performed the operation before where we decide, okay, this should be the optimal age, as a decision parameter, this should be an optimal
Okay,
height.
think firstly, what is the depth of the decision tree?
It's essentially like level.
For example, for this data, what will be the maximum depth of the tree that I can have?
Max is like level 3 essentially. Like height is 3, essentially level 0, 1, and 2. Yeah, so 2 decision parameters are there.
Yeah, I have the maximum depth can be number of features over it, correct?
Correct, yes.
All right, assuming that I have the binary split in the features also. All right, does it have to do with what are the heights over here?
No,
What are the different heights that we have?
no.
So number of features decide number of depth, no? So then why are you confusing it with the length of the list?
Like in like section 3 only, like it's initialized, right? In line 4, the depth is essentially a list of 1, 2, 3, 5, 6, 6, 7,
Where
and 9.
in section 3?
Yeah, train trees with different max depth, right? Section task 3.1, like which we were just discussing.
Okay, 3.1, 2.3,
3
3.1.
point-
Oh.
Yeah, this list.
Hmm.
Essentially,
I can draw this tree with a depth 1. I can draw this tree with depth 2 also, right?
correct.
What stops me for drawing it only at depth 1? If I have 10,000 features over here, how much is the depth decision that you will be taking?
Max number of features, right? 10,000 max.
Why? What if
Height.
after 10 feature only you have pure data? Then why would
Okay.
you be going up to 10,000? Does it make sense?
Hmm.
All right. It depends that what is the depth that you want to take. Maximum depth can be the number of features if they are binary in nature. All right.
But we
Doesn't-
iterate on.
Doesn't mean that if I have the 2 features as color and height over here, and third feature as the age of element, will you be taking this depth 3 now?
But like again, like the question comes like
My question first. Either you'll go over here and there. All right. If I have the color, if I have the height, if I have the age of the element, will you be going to depth 3?
like no. In that case, no.
Why?
right?
Why do you need to go? You don't need to go. You up to depth 2 only. You need to go, right?
Yeah.
So what should be your criteria to understand up to which depth you should go? That is, the accuracy is increasing. The data is becoming pure. You have good splits, and the accuracy is increasing. Does it make sense? If I have one more feature over here, color, height, age, and the address of the animal, would you be splitting it on the address?
Not
So
really.
why are you thinking the depth has to be 4 in that scenario? Surely.
But like coming there, we will be taking J for address, right?
We are taking at this depth 1.
Right.
Did I take a single feature only and I said that, okay, I'm going to divide it? I explored all the features now.
Right. We explored
So
all the
depth
features.
was 1. Depth was 1. First depth, I explored all the features. So how does the exploring of all the features at a particular stump is related to the depth? Two
Correct.
separate things that you are mixing. At
Correct.
each and every stump, I have to check whether which feature to do the split on. All right. That is exploring the features at a particular depth, at a particular stump. That has nothing to do with you are saying that, okay, if I'm exploring all the features, why are we taking these? I am taking these that, okay, should I be stopping the tree right here? Or should I be stopping the tree right here? Or should I be stopping the tree right here? Does it make sense? How do you decide how much depth of the tree I have to go? Till now, we have been doing only at a particular decision stump only. Now I'm exploring. At this decision stump also, I will be having the labels of my target now. Based upon this split, if I start assigning the labels, I can do that also. Who stops us? At this level, I can have the labels of the data as well. Whether it is 0, 1, 0, 1, 0. Make sense? So at this place, if the depth is 1, how much is the accuracy? I will be having lesser accuracy. At this place, I will have perfect accuracy for my given data. The hippo and the elephant one. Not the numerical one. The numerical one has noise. No matter if you go to the best depth, still you will be having some inaccuracy. Why? Because I have certain noise. Make sense? So we'll explore different depths. At different depths, how does my classifier is performing good? And I'm just going to run it. The understanding lies in, what did I do? All right. This, I didn't need to use anything over here. Okay. If I run it. Okay, that's fine. All right. I don't want to take 6. I want to take 7. I want to take 8. All right. Okay. If I want to take 9 also, and 10 also. Okay. Okay. Now what we observe is at depth 1, the training accuracy is 0.76 and the validation accuracy is 0.75. Just look at this data and tell me what will be your decision. This is you deciding upon how much is the maximum depth to give. That you are training your hyperparameter of how much depth to give to a classifier. What will be your decision and why?
Accuracy is 83% in the max depth of 8. That's the maximum. Oh, no, max depth of 5, accuracy is 84. Yeah.
Okay. Anybody? The accuracy is consistently increase. 5. And the reason?
Because in validation accuracy also we will see, right?
Okay. Give me a machine learning
After 5
engineer's
is
answer.
starting to overfit.
Perfect.
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 Yep.
This is the answer.
After 5,
This is what you have to say in the interview. Up to 5, the training and the validation accuracies are increasing consistently. But after that, the model starts overfitting. The training accuracy is more and the validation accuracy has started coming down. Model has started overfitting. That's why 5 will be my ideal situation for my depth of the tree. Cool. All right. And remember, this is numerical data. All right. It is not 2 features only. The split is based upon the feature as well as the threshold. On the same feature, I can have the different splits on different thresholds. Make sense? Because these features are not binary, they are continuous. So only for 2 features, I have multiple splits. Make sense? This is very simplistic data just to make you understand the Gini impurity. All right. So maximum depth can be even more than the number of features because the features are continuous and we are taking the mean of the thresholds. So different thresholds in the same feature can act as a splitting mechanism criteria. All right. Now we are going to see one more thing. This is one of the downsides of the decision trees, overfitting. Another downside that we have to see is the leakage. In the leakage, what we have done is to the training, I have leaked the data of I have given the label only. There is a particular name to it. If I'm giving the label only, then what is it called? What kind of data leakage is this?
Target leakage.
Target leakage. Make sense? So over here, after depth 5, literally the model has started remembering That's why it is giving 1 accuracy, training accuracy as 1, but the validation accuracy has gone for 6. If I am giving the training labels only to my decision tree, then basically it is going to learn those labels, those targets. In the validation also, we have leaked the data. Make sense? Now, if we run for a particular depth, a specific depth 3, a classifier which we have imported from my sklearn. If I train the model over there, if I try to fit the X training leaked data, then let's calculate the accuracy at that time with the leakage. If I run this, then the leakage accuracy will be 1. Did I get the accuracy ever as 1 at a depth 3? I was way off than 1. But now the model has learnt, because a little bit of leakage of my target, the trees are going to aggressively use that leakage. It's basically going to learn the labels. The second weakness of the decision trees that we have seen. And from tomorrow, we'll start seeing how do we fix that issue of overfitting of the data in the decision trees.
Can
We are
we say
Yep, go ahead.
leakage because of trees' greedy nature? Like it's essentially good.
We can
Oh.
say it's not because of the greedy nature. The leakage is happening, but trees do aggressively utilize it. All right. Because you have just leaked the answer to the student only, right? So it is going to learn it, and it doesn't scale any data, it doesn't change any data, it is just looking at the pure data itself. So if you have given the pure labels only, it is going to learn, oh, it is 0, 0, 0, 0, this is 1, 1, 1, 1. Make sense?
Okay.
You can relate it to the greedy nature of the decision trees also. All right. Anybody else? Yes, Ajay, go ahead. What's your question? We are
I
done
just
with the class. Yeah, go ahead.
So now that we have implemented decision tree, right? In interviews for ML coding rounds, is the expectation to implement all of these? Like, how do they
You should
ask?
know. You should know what is going on under the hood. That this decision tree classifier is doing nothing but all these steps under the hood. All right. Because once you come to know that how it is calculated, then you are more able to tailor it. All right.
When you say a stump, so it means a particular node with
Yes,
that
absolutely.
feature having a particular threshold and also depth at that node.
We do not need to know the depth at that node. We just need to
Okay.
know the randomness at that node.
Okay.
Make sense? All right. Anybody else? Any other question? Bye, guys. Have fun.